Today we're going to begin to learn about our last unit. Last unit is thermodynamics. Thermodynamics literally means the flow of heat, but we're not really in a position yet to know what that is because we don't really know what heat is. We talk about it in English a little bit, and we have two concepts that are sort of the defining concepts. So this is the beginning of thermodynamics. So we spend about 2 weeks learning thermodynamics, and then some of you are going to spend a whole semester doing it all over again in more detail. I am going to try to give you a really good, solid foundation and introduction so that, if you are one of those ones who has to take a thermodynamics class in the future, you'll have a pretty good starting place. However, that class will be much more intense than what we're going to do here. So the two concepts I was mentioning before are temperature and heat. In English, I think that we confuse these concepts a little bit because we have the word hot, and the word hot means high temperature and doesn't have anything to do with heat, but it sounds like heat, right? Heat and hot. And so I think linguistically we kind of muddle these two concepts. We can add to that the fact that historically no one really understood what they were for a long time. So we have, a sensation, we touch something, it feels hot or it feels cold. What we're actually feeling is the flow of heat. So if I touch something and it's hotter than me, heat's going to flow into me from that thing. And if it's colder, I'm going to lose heat. Heat's going to flow from me to that thing. And so what we're feeling is the flow of heat. And, the temperature is a little bit of a nebulous concept. We just know that heat flows from a hot thing to a cold thing. And so we kind of made historically these arbitrary temperature scales, which just allow us to put things in order. This is hotter, A is hotter than B, and B is hotter than C, and C is hotter than D, so A must be hotter than D. We put things in order, and we have degrees, but these degrees don't really mean anything. They don't have any content. We don't know what does it mean for something to, have a 1 degree of Fahrenheit or Celsius or Rankine or Kelvin, any of these weird temperature scales. Heat was not well understood. We didn't know what heat was. We knew that it's flowing because we can feel it. We feel it flowing. We also see the effects when we have a hot thing and we put it in contact with a cold thing. The hot thing shrinks. And so we see that and we recognize that that's associated with it losing heat, and the cold thing expands. And so originally the idea was that heat was some kind of a fluid, but it was a very special fluid. It was a mystical, invisible, odorless, tasteless type of fluid that just flows from one thing to another. And we couldn't ever, try as we may, we couldn't just take a hot piece of metal and squeeze it and get a cup of this fluid. But this fluid was called caloric. And the early model was that this mystical fluid is the thing that's flowing when we feel the sensation of heat flow. And it has some nice features. It explains why things expand when heat flows into them. They expand to make room for the caloric. So they kind of swell and bulge like a balloon. As they lose caloric or as they lose heat, they shrink because, as the balloon empties out, it shrinks. So it had some pretty good explanatory principle, but there were some problems because, for example, you could take a cold piece of metal like a drill bit and a cold sheet of iron, and you could start drilling a hole in that cold sheet of metal with that cold drill bit, and they would both get hot. So it was kind of confusing. How can we have two things that are cold, which means they must not have a lot of caloric in them? And then we put them together and we start drilling, and then all of a sudden they both get hot. So people talked about there was like latent heat. We still use that term in a different context, but there was this sort of pent up heat that's hidden. And when you start drilling a hole, you punch a hole in this balloon and it starts leaking out. The heat is leaking out. But it also happens if you don't have to punch a hole. You can just take your hands and start rubbing them together really fast. And when you do, they get hot. You can touch your face and your hands feel hot. So how did your hands were cold and clammy, you know, and then you rub them together and now they're hot. So where did the heat come from? So there are a lot of problems with that. Additionally, our sensation of temperature is just that, a sensation. And even Aristotle recognized that it was a little bit relative. He describes an experiment where you take 3 basins of water. You have one that's very hot water, like as hot as you can handle it, and one that's cold, very cold, as you know possible, ice water, and then a third one that's just room temperature water. You put your hands in the room temperature water, it's sort of, you barely feel it. It's just sort of neutral feeling. And then you put your hands, one hand in the hot water and one hand in the cold water, and you let them sit there. And it's really weird because one hand's hot and the other's cold, but your hands kind of get used to it. And then you take the hands and you plunge them back into that middle basin of room temperature water. And the hand that was in the hot water feels that that water's cold, and the one that was in the cold water feels that the water's hot. So it's kind of like mentally what's going on. You're feeling this water, and one hand is telling you it's burning hot, and the other is telling you it's freezing cold, but it's really the same. So there's a lot of problems with this early model. Again, what temperature told us is just a way of ordering, you know, rank, order. You don't even have to write this down, but rank ordering the relative hotness or coldness. My pen tool's having a little trouble of things. So again, if I have something that's 52 degrees Fahrenheit and something else that's 53 degrees Fahrenheit, I know that heat will flow from the 53 degree temperature object to the 52 degree temperature object if I bring them into contact. But I don't really have any reason to suspect that the difference between 52 degrees and 53 degrees is the same thing as the difference between 70 degrees and 71 degrees. No real reason that's the same. So then we get a more modern understanding of temperature and heat. And now we recognize that temperature is, so this is old, and this is new. I'm going to call it new because it's really 19th century. So we're in the 21st, so it's still kind of old, but not as old. And we say that temperature is a measurement of the average kinetic energy of the particles of a system. So we have this picture that if I have something hot, that means its particles are moving really fast. If it's a solid, that, you know, solid particles are connected to each other, but they're vibrating really fast if they're hot. And if they're cold, if they're low temperature, they're still vibrating, but they're vibrating slowly. And the colder they get, the slower the vibration becomes. And if they're liquids, you know, the particles, if it's cold liquid, they're sort of moving, rolling around each other slowly. And as it heats up, they're doing this faster and faster, rolling, and eventually you get them so hot that they break free, and now they're gas molecules. So we have this picture, and we're going to try to prove this picture as we go. And for heat, then what heat is the total kinetic energy of the particles of a system. There's kind of 2 usages for heat. We can mean the total amount of kinetic energy of the particles, that's how much heat something has, or we sometimes talk about the flow of heat. So when heat flows from one thing to another, we mean the total amount of kinetic energy that flowed, that transferred from one system to the other system. So it's, again, linguistically, we can still, with this modern understanding, confuse it. So I want to just point out or illustrate that we can have things that have high temperature but low amount of heat. And we can have things that are low temperature with a lot of heat. And, obviously high temperature and high heat we can have, and low temperature and low heat. So let's try to make a little grid here. We can have things that are high temperature or low temperature. We can have things that are high heat. We use the symbol Q for heat, and low heat. So something that's high temperature and high heat is very easy. We've got to get something that's a high temperature and that also contains a lot of heat. So we could say maybe the core of the Earth or the sun. These are things that have a lot of heat and are also very high temperature. But it's a little harder to think of something that has a lot of heat but is low temperature. Can anyone think of an example that would be something that's cold? If you touched it, it feels cold, and yet there's a lot of heat energy stored in it. Killian?
What about the ocean?
Yeah, that's a good example. That's probably one of the best examples. So the ocean is, it's pretty cold, to be honest. Most places, you can find a few places where the water's somewhat warm, but most of the ocean's very cold. And yet, if you dump a cooler of ice in the ocean, it's going to melt all the ice very quickly. In fact, you could take all of the ice in the United States and dump it in the ocean, and it will all melt. So there's a lot of heat in the ocean. All of the hurricanes that we're getting, increasingly, every year are basically coming from heat energy in the ocean as the ocean gives up heat. As the world cools, the ocean is giving up more heat, and that heat fuels these tremendous storms that have a lot of energy. So, okay, that's a good example. How about something that has a high temperature? It's hot, but it doesn't have a lot of heat. Does anyone have an idea what could be, hot? If we measure it with a thermometer, it will come out as high temperature, but not enough heat to even maybe melt a single ice cube. Killian?
Maybe like the drill bit.
Okay, yeah, that's a good example. That drill bit, we drill into a piece of steel, it gets really hot. If you touch the drill bit, you'll burn yourself. But if you set the drill bit on an ice cube, it's going to kind of go, and it will start kind of melting into the ice cube a little bit, but not very much before it cools off and it's cold to the touch. So that's a good example. Hot drill bit. Another example that I like would be maybe just a milliliter of boiling water. So boiling water is hot. It's 100 degrees Celsius. Doesn't matter how much of it. It's always around 100 degrees Celsius. So it's hot to the touch. It can burn you, but 1 milliliter of boiling water isn't going to do too much damage. If it splashes on you, it may hurt like, ow, but then it cools right away because it just doesn't have that much heat. And then, of course, something that's low temperature and low heat, I don't know, an ice cube. Ice cube is low temperature and also doesn't have a lot of heat. You can't really use melting ice as your criterion for having heat because ice is cold to us, but it's warm to dry ice. Water ice in your freezer is relatively warm compared to a chunk of dry ice or liquid nitrogen or something else that's very cold. So the main idea here is things that have high heat are large, and things that have low heat are small. That's really what makes the difference. If something is small, it doesn't matter how hot it is. It can't really have that much heat because there's not enough particles to store a lot of energy. On the other hand, if something is really large, even though the average kinetic energy of its particles may be very low, there's just so many of them. When you add them up, it winds up being a substantial amount. Okay, so another difference between heat and temperature. If I have something that is high temperature and I break it in half, each piece is still at the same temperature. So the temperature doesn't subdivide. I have a chunk of hot metal, I cut it into 5 chunks of hot metal, and those chunks are all the same temperature, more or less. Maybe because of the cutting action, maybe I change the temperature a little bit. Whereas if I have something with a lot of heat, like let's say the ocean, and then I subdivide it, I take just an empty cup and I scoop some ocean water out of it. Now that cup, the temperature is the same for the water, but the amount of heat has subdivided. So, that's a difference between the two concepts as well. Now, today we're going to talk about really two things, and I don't want to go too far. We're going to talk about temperature scales and what happens when we change the temperature, how we measure temperature, things like that. And then we're going to talk about how heat can be transferred from one thing to another. So first, let's talk about temperature scales. So we use the Fahrenheit scale here for a lot of purposes. And the Fahrenheit scale is a temperature scale, as you guys probably know, that's built around the freezing point and boiling point of water. So water freezes at 32 degrees Fahrenheit, and water boils at, does anyone know the boiling point of water in the Fahrenheit scale? You guys don't remember that one? So we don't need to know that, because when you want to, make some pasta or some rice, you just put the water on and you turn it on, and when it starts boiling, it's hot enough. We don't really care. But we're really intimately familiar with this 32 degrees Fahrenheit because we're all secretly looking for that number, hoping we have a snow day. Okay, so we have 212 degrees Fahrenheit is the boiling point. And this is a difference of 180 degrees. So basically, if you want to build a thermometer, what you do is you take a tube, you fill it with mercury, and then you seal it up. You put it in some freezing water. So you've got kind of water and ice mixture. And when you do that, you see the mercury sort of contracts and it gets to a certain level. And you put a line there. And that line says 32 degrees Fahrenheit. And then you do the same thing with boiling water. You put it in boiling water and you see the mercury expands. It goes up to a certain level and you mark that line and you call that 212 degrees Fahrenheit. And then you simply subdivide that distance into 180 equal bits. And we call those the degrees. And again, it doesn't really mean that what happens between 32 and 33 degrees is exactly the same as what happens between 211 and 212. That's not necessarily true, but it's just a way of putting things in order. And we, of course, also have the Celsius scale. I'm sure you all are familiar with this scale as well. We learn about that in school, and if you've lived in another place, you probably just used this scale. And for this, we have basically the same 2 points. We fix it around the freezing and boiling points, but the numbers are different. This is an attempt to make it a little more metric. So water freezes at 0 degrees C and it boils at 100 degrees C. And so that means there's exactly 100 degrees between freezing and boiling. So that feels a little more metric, but to be honest, neither one of these scales is particularly good, okay? They're both okay. They work for a lot of purposes, but I wouldn't say that the Celsius scale is better or worse than the Fahrenheit scale. They have their advantages. Fahrenheit scale, the size of the degrees is a little smaller, and it's a little bit closer to what we feel with our hands. When we feel, when your child is 99.6 degrees instead of 98.6, 1 degree too hot, and you feel their forehead, you can feel that difference. And 1 degree Celsius too hot is already a pretty big difference. Neither of those scales are what we really want to use. However, sometimes they're what we have. So we want to know how to convert between one and the other. And again, I'll go over this quickly because I'm sure you've all seen this at some, maybe middle school science class or something before. But in case you don't remember the formula, it's the 180 to 100 degree ratio is key. That's a ratio of 9 to 5. So the size of the Fahrenheit degrees is 9/5 of the size of the Celsius degrees. However, they don't have 0 at the same time. So we have to add a 32. To be honest, when I'm trying to do this formula, I never really am 100% sure of it. So when I write it down, I know there's a 9/5 or a 5/9, and I know you add or subtract 32, but I always like to check it and make sure when I write it down that it's correct. So you check it by plugging in 0 degrees Celsius and making sure you get 32 degrees Fahrenheit. So if I plug in 0 degrees Celsius, I definitely get 32 degrees Fahrenheit. And then we check it again at another temperature, like 100 degrees Celsius. I know 100 degrees Celsius, it should be 212. And so if we plug in 100 degrees here, 100 times 9/5 is 180, plus 32 is 212. So, that's how you check it. Other points that may be useful to remember for checking is that these two temperature scales have the same exact temperature only at one point. Negative 40 degrees Celsius is the same as negative 40 degrees Fahrenheit. So if we put in negative 40 here, we should get negative 40 back. Also, human body temperature is typically quoted as 98.6 degrees Fahrenheit, which in Celsius is exactly 37 degrees Fahrenheit. So that's kind of a useful number to remember. If you're traveling and you're in a place where they use Celsius instead of Fahrenheit and you don't know what the temperature is, and you look at the bank and it says this is the time and it says the temperature is 40 degrees Celsius, as soon as it gets above 37, it's pretty hot. So anything hotter than human body temperature is typically going to be not so comfortable. Okay, however, those are our temperature scales. If we want to convert the other way, we just do algebra on this formula and rearrange to solve for TC. We would get TC equals 5/9 times T Fahrenheit minus 32. I will not give you both of these equations. I will just give you this one and allow you to do the algebra if you need to go the other way. But we want to use the third scale, and even this third scale, I'm sure most of you have learned about it in some other science class, maybe chemistry, maybe high school science of one sort or another, and that temperature scale is called the Kelvin scale. So the Kelvin scale comes out of doing some experiments with gases. If you take a gas and you plot the pressure versus the temperature at constant volume, okay, so if we fix the volume, so that's easy to do, right? You just have like a pressure cooker or something. You seal the lid and it doesn't let air in or out. And you raise the temperature. And as you raise the temperature, you see that the pressure goes up. It's linear. It's a linear relationship. You put a different gas in there, do it again, you get the same thing, but maybe a different slope. You keep doing this. Maybe you use different amounts and so forth. If you do it enough times, you notice that these curves, if we project them backward, they all seem to go to the same point, okay? And my data don't necessarily look perfect, but if you do it with, very carefully, they really all point to the same temperature. So that's a little provocative. It seems to indicate that there's some kind of magic temperature at which the pressure of any gas is going to be 0. So if we think about, now we understand what temperature is, it's the average kinetic energy of the particles of the gas. Well, what does it mean if we have no pressure? It means our gas particles, where does the pressure come from? It comes because they hit the walls of the container. They're flying around and they hit the walls, they bounce off. So if we get no pressure, it means there must be no collisions. No single particle is going to hit the walls of our pressure cooker. And that means that nothing's moving, okay? The particles are frozen completely. They don't move. They don't even vibrate. And so that, in terms of our modern understanding of temperature, that would correlate with the average kinetic energy of the particles being 0. So no particles are moving. The only way the average kinetic energy can be 0 is if every particle has 0 kinetic energy. because kinetic energy is always positive. So you can't average over positive numbers and get zero. You can only average over zero numbers to get zero if nothing is negative. So there's a reason to think this is the coldest temperature we can get. So this is called, well, first of all, it's negative 273.15 or 16, but I'm just going to round it to negative 273 degrees Celsius. And we call this absolute zero, meaning that's as cold as we can get. For theoretical reasons, it doesn't make sense for anything to be colder than that temperature at which the pressure would be zero. So the Kelvin scale just draws the axes over so that that point is at the origin. And by what we're doing is we're just moving the origin 273 units to the left. And so the temperature on the Kelvin scale is equal to the temperature on the Celsius scale plus 273 degrees. So that is the size of the Kelvin degrees is the same as the size of the Celsius degrees. There's still 100 degrees between freezing and boiling points of water. There's a fourth scale called the Rankine scale that does the same thing as the Kelvin scale but uses Fahrenheit degrees. So it puts the zero at the same place, but the size of the degrees correlates with the size of Fahrenheit degrees. No one really uses that scale anymore. So that's just kind of a curiosity. But if you're looking in the library and you're going through old books, you may see reference to that temperature scale. Okay, how many of you, raise your hands if you have seen the Kelvin scale before? Okay, so a lot of you have seen it. That's good. So when do we use the Kelvin scale? When do we use the Celsius scale? There's a really nice general rule for this. We're going to use the Celsius, well, let's just say TC, whenever the formula contains a delta T. Okay, so if we have a physics formula that involves delta T, then we're going to use the Celsius scale. However, if the formula contains T alone with no delta, we must use T Kelvin. There's not a deep reason for that, other than that the way the formulas are written are all such that if we only have a T, we better use Kelvin. They're sort of designed that way. But if there's a delta T, because the size, if I change 5 degrees Kelvin, I also change 5 degrees Celsius, then we can get away with just using the Celsius temperature because the size of the delta T's would be the same anyway. Okay, so as we go forward, we're going to see probably half of the time the formulas, maybe a little more than half the time, have a delta T, but sometimes they just have a T. If they just have a T, we better use Kelvin. Okay, any questions? Okay, so that's all, stuff you probably know, but let's learn a little bit more. The way we measure temperature historically is by thermal expansion. You heat up the mercury and it expands. You cool it down, it contracts. And so for thermal expansion, when we heat something up, there's a change in length. And that change in length is proportional to the original length. And it's also proportional to the change in temperature. So if I have a piece of metal that's 1 meter and I raise it up 5 degrees Celsius, I'm going to see a change in temperature. If I raise it another 5 degrees Celsius, I'm going to see that same change in temperature. I'm going to see the same change in length. If it's a 2 meter long rod, for a 5 degree change in temperature, the change in length will be twice as big as for a 1 meter rod. Okay, so the size of the delta L is proportional to the length. And what we say, remember this weird symbol is the proportional to. It's kind of like 3/4 of an infinity sign. And I'm pointing that out because just sort of in poor planning, in the case of the physics community, when we write this as being equals to a constant times, the constant that's used is a Greek letter alpha. I know that looks a lot like my proportional to symbol, but this is the alpha like for angular acceleration. However, in this case, it is called the coefficient of linear expansion. It's a number we look up. Okay, it's a number we look up. And let's just do a quick example. If we have a 100-meter steel tape measure, so 100 meters at, let's say, 15 degrees C, what is its length at 40 degrees C? So the alpha for steel is 12 times 10 to the negative 6 degrees Celsius to the -1 power. So the change in length would be equal to the initial length times the value of alpha, 12 times 10 to the -6 degrees Celsius to the -1 power, times the change in temperature, which in this case would be 25 degrees Celsius. So those inverse degrees Celsius cancel my degrees Celsius. And it's going to be 0.03 meters. So the L in general is going to be the initial length plus the change in length. So that's going to be 100.03 meters. So it will grow by 3 centimeters. So that may seem like it's not much, but if you're in construction, when you measure something and your tape measure is a little longer than it should be, then you're going to be measuring things a little shorter than they should be. So it becomes particularly important with things like building bridges, where you have very long cables, very long steel beams, or building the St. Louis Arch. If you're from or around St. Louis, you might have seen the story that the St. Louis Arch, when they were building it on the last day, they're ready to put the last piece in at the top of the arch, and it didn't fit. I just would love to see, I wish someone had captured the facial expression of the foreman the moment he realized that they built the two pieces a little too close together, the two arches, you know. But they, of course, realized it was because of thermal expansion. They got a bunch of fire trucks out and hosed down the arch to cool it off. And once they cooled it off enough, they could get the piece to fit. They put it in, welded it in place, and left it. But that must have been just a really terrible sinking feeling when they first saw that someone made a miscalculation somewhere. But they figured it out. Okay, so technically we could write the length equals initial length plus delta L. And by using our formula, this is L naught plus L naught alpha delta T. And we get L naught times the quantity 1 plus alpha delta T. So we have a formula for the new length given the old length. And we can actually use this to see what happens to an area. Okay, so suppose we make an area and maybe it has a length and a width, an initial length and an initial width. And then we want to maybe heat it up. And when we heat it up, it's going to expand. And we're going to get a new length and a new width. And we want to see how does the area expansion work. So the area is just going to be the new length times the new width, but the new length would be the old length times 1 plus alpha delta T. And the new width would be initial width times 1 plus alpha delta t. And what we get is L naught times W naught times 1 plus alpha delta t quantity squared. So that means the area is equal to the initial area times, if we FOIL this out, we get 1 plus 2 alpha delta t plus alpha delta t squared. Now, customarily, because alpha is typically a very small number, like a 10 to the minus 5 or 10 to the minus 6 kind of number, alpha times delta t is usually still a small number, unless the delta t is in the thousands of degrees or tens of thousands. And so if alpha delta t is small, then we can say alpha delta t squared is very small. And ignore it. So we get A equals A naught times 1 plus gamma delta t, where gamma is equal to 2 alpha and is called the coefficient of area expansion. Instead of linear expansion, it's area expansion. Now, typically when we're looking up these values, we're not going to find a table of gamma because we just take alpha and multiply it by 2. So when you're looking in the table, you're going to find the alpha for steel. And if it's a sheet of steel, then we want to know how the area of that sheet expands. Then we just multiply the alpha by 2 and use the same kind of formula. And for volumes, let's see. So we get, got a shape and we make it into 3 dimensions. Okay, about like that. We have an initial length, an initial width, and initial height. We can do the same thing let it expand. Into a larger shape where we have a new height and a new length and a new width. And if we do the same type of thing, you can show, this is going to be for extra credit. I'm just feeling so giddy that the semester's almost over that I'm getting a little extra credit crazy. This is a very easy extra credit, but you can show that the volume is equal to the volume naught times 1 plus beta delta t, where beta equals 3 times alpha. So you're going to do basically the same thing that I did for the areas, where you're going to write this out and then you're going to simplify and you're going to throw out anything with alpha delta t squared or alpha delta t cubed. And what's left is just going to be 3 times alpha times delta t. So this is a very easy extra credit. My college physics students do the same extra credit, but you guys can understand it at a little bit deeper level. I want to show you something that's maybe from a math standpoint a little bit cool. So I wrote that L equals L naught times 1 plus alpha delta t. And we have A equals A naught times 1 plus alpha delta t plus 2 alpha delta t plus alpha delta t squared. And for the volume, we get something like volume naught times 1 plus 3 alpha delta t plus 3 alpha delta t, squared plus, stuff. It just kind of keeps going. This looks a little like something. Does it look like something to you guys at all? what I'm thinking about is how we have kind of a constant term and then an alpha delta t and then alpha delta t squared and even an alpha delta t cubed and to the fourth power and so on. It looks a little bit like a Taylor series. And in fact, this formula for the length is not really correct. It should say plus alpha delta t squared over 2 factorial plus alpha delta t cubed over 3 factorial and so on. It's really just the first 2 terms of a Taylor series. And we just throw these guys out. We throw those ones out. And the area expansion is the same way. In fact, if I kept more terms in the Taylor series, if I kept these guys in my series for L, then this term here would be different. It would have a different coefficient, okay? So technically, we can't really keep these guys if we didn't keep those guys. If we didn't keep the alpha delta t squared terms on the length, we definitely cannot keep them on the area or the volume. If we do want to keep them, because we want a little bit more accuracy, then we need to keep more terms for the length. So what this means is, if we use linear expansion for measuring temperature changes, it only works in a small temperature range. It only works while alpha delta t is small. If alpha delta t gets bigger, then my change in length is technically L naught alpha delta t plus L naught alpha delta t squared over 2. Okay, and then that's not linear. Once alpha times delta t becomes big, then this becomes the biggest piece. So all thermometers have this built-in problem that they're only accurate in a small temperature range. That's whether you're using thermal expansion or maybe in a modern digital thermometer, we use the resistance of materials. Resistances also are proportional to changes in temperatures, but they also have a similar Taylor series. And so the same problem occurs for a digital thermometer. You have to zero it out at a certain temperature, and then it's going to be accurate in a range around that temperature. But that range, the farther you get from that temperature, the less accurate it gets. And that's why you can't go, like if you like to cook, you can buy an oven thermometer and you can buy a candy thermometer and you can buy a thermometer for measuring if you're sick, but you can't find one thermometer that does all 3 of those things because they each only work in a small temperature range. Okay, that's just kind of for the sake of enrichment. One last thing to mention, and then I'm not going to spend a lot of time today on the thermal expansion, but it's what happens if we have a sheet of something, an area, and we cut a hole in it, and then we heat up the sheet. What happens to the hole? Does the hole, I think there's 3 possibilities. Anyone have a guess what happens to the hole, to the size of the hole if we heat up a sheet of metal with a hole cut in it? What's one option? What's one possibility?
It could shrink.
Okay, it could shrink. What's another possibility?
It expands.
Yeah, it could expand. And is there a third possibility?
Stays the same.
Yeah, nothing happens. Think about it for a minute, and I want to vote. I want to take a vote and see what you think. Okay, let's just vote. Whatever's your best guess. Use your computer hands to vote. Who says the hole shrinks? Raise your computer hand if you think the hole shrinks. Let's see, 3 computer hands. Okay, now raise your computer hand if you think the hole gets bigger. 3 people. And I think that's everybody, but does anyone think nothing happens to the hole? Raise your hand if you think nothing happens. Okay, let's go ahead and take a short break. When we come back, we're going to answer this question. All right, well, I was actually hoping, I thought I had around here a little demo item that I could use to show this to you, but I couldn't find it. So I just have to tell you what happens. I think it's interesting because I could see any of the three being the case. I mean, we could think, hey, the hole should shrink because the metal's going to expand into that space. But we could also think, well, it expands because as the piece of metal expands, the hole is expanding too. And we could think nothing happens because how does a hole change when you change the temperature? Turns out that the hole expands. And the reason it expands is because the same reason that the metal grows in the first place. You've got these molecules and they're sort of holding on to each other and they're vibrating. But they're not actually touching. They're connected by forces. And those forces are sort of spring-like in nature. So just imagine you have a bunch of blocks connected with slinkies and you start vibrating one of them. The slinkies start to vibrate and in general, they're going to stretch out a little bit. And these guys all want to move away from each other. So as we heat the metal or the solid, whatever it is, its molecules all want to move away from each other. And so if we consider the molecules that are around the edge of this hole, they want to move away from each other. It's basically like you're in a big crowded auditorium and it's in the middle of a pandemic and then someone in the middle sneezes. Everybody wants to move away from everyone else, create a little more distance. Well, you're not going to move into the middle because if these guys move into the middle, they're getting closer together. Nobody is going to get closer to anybody right now, right? So they're all going to move back. And by moving back, they're farther from each other. And the molecules behind them also back up. Everyone backs up until at the very end, you know, at the edge, every molecule backs up. And so, yeah, actually the hole will grow. And this can be pretty useful if you, let's say you have like a nut or something on a bolt and you want to get it loose. It's really tight. Well, you can heat it up, and as you heat it up, the hole is going to expand. Of course, also heating it up probably breaks down some of the gunk that may be making it freeze in place. But plumbers also use this trick to attach pieces of pipe to other pieces of pipe. You can take a metal sleeve that's not quite big enough to fit over two sections of pipe. And then you can heat it up with a torch so the hole gets bigger, and then you're able to slip the two pieces of pipe in. And then when it touches them, they're going to come in thermal equilibrium. So that metal sleeve that you heated up is going to cool off. And when it cools off, it shrinks, and its natural, inner diameter is maybe smaller than the outer diameter of those other pipes. And so it basically gets locked in place, and it's never going to come off unless you can somehow heat it up again without heating up the other pipes. So it's a pretty cool trick to join things together by using this thermal expansion. Okay, so I'm not going to go any further with thermal expansion right now, but I do want to talk about, just briefly, mechanisms of heat transfer. So mechanisms of heat transfer. So we have three main mechanisms that we talk about. And in this level, we generally only do problems with two of those. The first one is called conduction. So this is primarily the mechanism of heat transfer in solids, although it also does occur with liquids and gases. The main idea is you've got a bar of metal. Okay, so let's just imagine we have a bar of metal. And we put one side in the fire. gets hot, right? So we've got a hot temperature here. And over on the other side, we have a cold temperature. Maybe we rest this on a block of ice. Okay, so it's cold. What's going to happen is the molecules that are in the fire, they're going to start vibrating really fast. And their neighbors, they're connected via these spring-like forces. And so they start to kind of pick up the vibrations and they start going faster. And then their neighbors start picking up the vibrations. And so the heat travels through the matter through these vibrations. And this can be even sped up if you have things like a metal where the electrons in the metal, in the atoms, are sort of only barely bound. They're very free to start moving around. That's what makes them good electrical conductors. They also, those electrons can get kind of kicked out of the atom, and then they fly through the metal and they have collisions, and so they transport the kinetic energy. So we can think of this as transport of the kinetic energy through collisions of particles and molecules. So physical contact between the particles, whether that physical contact is a bond that they share or whether it's an electron bouncing around. The rate that the heat flows, so we call this a power, dq dt. We call it a power. Well, it's proportional to the difference in temperatures between the two sides. And it's also proportional to the area that the heat is going to flow through. So that is, if it's a very fat piece of metal, it's almost like it's a pipe and it's fluid flowing through the pipe. You get more fluid flowing through a fat pipe than a small pipe. And so the bigger the cross-sectional area, the faster the heat can flow through. And it's inversely proportional to the length, which is the distance that the heat has to flow. So we could think of this maybe like, think of a window. A window, if it's hot, maybe inside and cold outside, you're going to lose heat through the window. It's going to flow from your inside warm house to the outside cold air. And the bigger the area of the window, the faster the heat's going to leave. Okay, so if you have a great big window, maybe you have a sliding glass door or something, that room is going to be very cold compared to other rooms because the area is big. On the other hand, the length, that would sort of be the thickness of the glass. The thicker the glass is, the slower the heat will be lost. Although glass is not very good at preventing heat loss, and so even having a thick piece of glass doesn't do you much good. Not as well as having a thick layer of insulation in the wall. But for the wall, the thicker your insulation is, that's a bigger L is, the smaller the rate of heat loss will be. So when we write this with a constant of proportionality, it's proportional to all these things. So we can say it's equal to a constant times the area times T hot minus T cold. This is technically a delta T, so we can use Celsius degrees here over the length, where the constant K is called the thermal conductivity. And I'm going to look up the values for a few things just to give you an idea. But for metals, this is typically going to be a very high number. And for an insulating material, it will be a very low number. So for copper, Cu is copper, the coefficient is 385 watts per meter degree Celsius. That means that the rate of heat loss is 385 watts for every meter of, what's really square meters per meter. So for every square meters per meter and per degree Celsius temperature change. So if you had a copper plate instead of a window, it would lose heat so fast. We can even calculate that. For glass, it's much better. It's 0.8. You might think, hey, that must mean this is a pretty good insulator, but that's even still pretty big. For air, it's 0.024 watts per meter degree Celsius. So let's see with glass, for example, what is the rate of heat loss for a chilly day? So on a chilly day, maybe the temperature, cold temperature outside is 5 degrees Celsius. And the temperature inside your house, that would be the hot temperature. Maybe you keep it around 20 degrees Celsius. That's a little cold maybe, but you know, maybe you live with old people. Old people like to keep it cold. So suppose the area is 1 square meter. We're going to find the rate of heat loss through the window. So we have the power is K, A, oh, windows typically a 1/4 inch glass, 1/4 inch. Ka times T hot minus T cold over the length. So the length, let's figure that out. That's 0.25 inches, and 1 inch is 2.54 centimeters, and 100 centimeters is 1 meter. That's 0.00635 meters. That would be in meters, the thickness of a 1/4 inch piece of glass. So that's going to be 0.8 times 1 times the temperature change 20 minus 5, that's 15 degree temperature difference over 0.00635. That is 1,800, let's just round it to 90 watts. So that means if you have a space heater, an electric space heater that's a 1,500 watt space heater, that's the highest that I've seen on space heaters, it's not even enough to keep you from losing heat with a 15 degree temperature difference. Okay, glass is a terrible idea. It's beautiful to have nice sunlight coming in, but it's terrible to keep when you want to keep your house warm. So what you can do is you can get double pane windows. When you get double pane windows, you have 2 sheets of glass, but it's not the 2 sheets of glass that's important. If I have 2 sheets of glass, that's kind of like doubling the thickness of the glass. That might reduce the power loss to, 945 watts, but that's still not great. The key to the double pane glass is that it has a layer of air between the glass. And suppose we have a 1/4 inch air gap. For a 1/4 inch air gap, I'm going to ignore the glass entirely. Next time when we come back, I'll show you how to generalize this for multiple layers. But for today, just to make a point, if we ignore the glass and just count the effect of the air, we use the same formula, but our thermal conductivity is 0.024. 57 watts is the power loss through that, just because of that air. When we add in the glass, it's going to shave a few watts off of that, but not much. So you could keep this room warm with a 60 watt light bulb. which costs you almost nothing. Or you can have one pane of glass and get a space heater, and the space heater still will not keep it warm. The temperature is going to go down from 20 degrees C to probably something like 17 degrees C, or so that you can get the power loss to be equal to the power that your heater's putting out energy. And that's assuming you don't lose any heat through the walls, which is a bad assumption. You're also going to lose heat through the walls, through the roof, maybe through the floor. So at any rate, double pane glass is a really good idea. And if you can't put in double pane glass, I've done this myself. Before my current house, we had a house in University City, and it had like a sliding glass door, but it was a double sliding glass door. So it was like 12 feet of glass. And the living room was freezing. No matter how hot we turned up the heat, it was freezing. So I just put a layer of plastic over it to make, to make another layer. But the problem with putting one layer of plastic is there's still about 3 or 4 inches between that plastic and the glass. And the air is only working as a good insulator when we're talking about conduction. If the air can start flowing around, we get our second type of heat transfer, convection, and then air actually takes the heat away pretty quickly. So I put one layer of plastic, and then I got a 1/4 inch like foam weather stripping, and I kind of put little 1/4 inch tabs all over this piece of plastic, and then I put a second piece of plastic on. So I basically made my own double pane plastic to put over the window, and it kept it so nice and toasty warm. I mean, it was amazing the difference it made just with a couple dollars worth of plastic. It looked really junky, but it was warm, And of course, double pane windows do the same thing, but they look nice. So next time I'll show you how we can combine layers, but I want to take the remaining time and talk about our other 2 mechanisms of heat transfer. So the second mechanism is called convection. And we're just going to talk about this on a qualitative level, not with any calculations. The calculations are somewhat similar, but you have to know a little bit more about the type of fluid, whether it's air or water or what, because typically convection is the primary mechanism in fluids. And you have to know about the viscosity and a lot of stuff. So this is how it works. Suppose you have a window on the wall and it's cold and there's air in the room. So the air kind of brushes the window and it gives heat up to the window. And when it does, it gets cold and it sinks, because as it cools, it gets more dense and therefore heavier. And it sinks and it's going to flush up some other air to just push it around the room. And that's ultimately going to lead hot air from the upper levels of the ceiling to come down and go past that window. And as that hot air goes toward the window, it's going to give up its heat and it's going to cool. And you get these circular currents going out throughout your room. And so convection is the flow of heat through the bulk motion of the fluid. In other words, it's not coming just because of collisions of molecules. For a gas, collisions between molecules happen rarely. That's why air is such a good insulator. But if the air can move, it doesn't have to collide to take your heat away. It just takes your heat and then it moves away from you. So convection can be fast. We can also see convection in the winter if we have a pond and maybe the pond is, full of water, and the water, the temperature at the bottom is comparatively hot. The temperature underground tends to be in the 50s in degrees Fahrenheit. Once you dig down about 6-7 feet, it just stays constant to a pretty good depth. And the temperature of the air in the winter is cold. And so what happens is the water, when it touches the cold air, it gives up heat and it cools. And so we get this, these cool currents of cold water going down, and then the water that's warm from the bottom rises and then it gives off its heat. And so we get these circular currents. In fact, when the temperature outside changes a lot, supposedly it's good for fishing because the water starts turning over quickly and that oxygenates the water, and it makes the fish high or something. They get really nuts because they get so much oxygen, and then you can fish and catch a lot of fish. I don't really fish, but I've heard that. At any rate, that's coming from circular patterns, and we even see these circular patterns in weather. We get hot, warm fronts and cold fronts, and when they meet, they can create sort of circular pattern that can lead to things like tornadoes. So that's convection. If we can make sure the air doesn't move, it's a great insulator. This is, in fact, why we have hair on our heads and why animals have fur. The hair, it doesn't really insulate you on its own, but it traps air. And a layer of air that's trapped is a very good insulator. This is also why things like down comforters or down coats, the down is very fluffy and it traps a lot of air. By itself, it's not a good insulator particularly, but it traps air and becomes a great insulator. And if you think about like fiberglass insulation in a home, the fiberglass itself, it's like glass. It's not really a very good insulator, but it's fluffy and it traps air in it. It's like cotton or something. And then that air layer creates a very good layer of insulation. We also wear clothing for the same reason. That's one of the reasons anyway, that the clothing traps air close to your skin, and that helps you preserve your body temperature. And if you're cold, you can just put on more layers, and each layer is going to trap a little bit of air in between it and the last layer. And then, several layers is going to make you nice and warm, even if it's not the most, fluffy, it's not a down coat or something that you perceive as really warm. Just having layers of anything. It could be anything. Okay, this leads us to the third form of heat transfer, and it's radiation. So radiation is happening for all phases of matter. Solids, liquids, gases are all radiating all the time, but what's special about radiation is it can travel through a vacuum. So that makes it really different. Almost all of the heat energy on the Earth is coming to the Earth in the form of radiation, traveling through the vacuum of space from the sun. So we get a lot of energy. Sunlight is something like 1,300 watts per square meter when the sun is directly overhead. So that's a lot. That's a lot of heat gain. So if you have a lot of windows, that can be good if the windows are on the side of the house facing the sun and you're letting sunlight come in. Then you can actually gain a lot of heat through the sunlight. And some people build homes this way. They have a lot of windows on the south side of the home, and then they have a lot of mass, maybe brick inside or stone inside the house. And that brick or stone sort of captures the sunlight and warms up, and it holds the heat for a long time. And then at night, that stone can radiate the heat back into the house. So that's a very good energy efficient way to build a home, especially if you have it partially underground. If the north side is underground, where the temperature is maybe 75 degrees, and the south side is where the sun comes in, is collecting the solar light. And then additionally, you plant trees on the south side so that in the summer, the trees they get a lot of leaves and they block the sunlight. But in the winter, they lose the leaves and they let the sunlight in. So by sort of doing that, you can build a house where you really don't need to spend any money to heat or cool it because it's sort of naturally happening. But you have to put a lot of thought into it ahead of time, into that home design. So radiation, the rate of power for radiation is proportional to the temperature to the fourth power. And notice this is just a T, not a delta T. So we're talking about an object that's hot. And when it's hot, it starts to glow. Think about the burners of an electric stove or oven, or inside a toaster, or even maybe just the coals of a fire. When they get hot, the fire may go out, but the coals are still hot and they're glowing. It doesn't have to be glowing invisible light, though. It has to be pretty hot to glow visibly. But if you turn on the electric burner on a low level, you can put your hand near it and tell that it's hot because you feel that radiation coming off of it. It's just infrared. We can't see it, but it's there. And you may think that's hot air rising, but it's not. There may be some hot air, but You can put your hand next to something that's hot and you will feel the heat radiating off of it. And again, it goes proportional to the temperature at the fourth power. Because it's not a delta T, we have to make sure we're using Kelvin temperature here. It's also proportional to the surface area. So this is a different, we still use A, but it's not the cross-sectional area. It's the total surface area. So the more surface area something has, the faster it's going to radiate. This is, why like a heat sink in a computer, if you look at it, it's like a piece of metal with a lot of sort of surface area for its volume so that it can try to radiate heat very rapidly. A radiator in a car or in an older home does the same thing. It tries to have a lot of surface area to be able to either add or subtract heat quickly. And then it's proportional to a number called the emissivity. So this is a number between 0 and 1 that tells us how good something is or bad it is at emitting light. But it's a little bit deceptive because emitting light, when we see something that is brightly colored, that's reflected light. Most of the things we're looking at are in reflected light. And when something appears blue in reflected light, what it means is absorbing other colors in the spectrum, but it's reflecting the blue light and we see it. So something that's blue is not emitting blue light. It's actually absorbing all of the colors but blue. If we make it hot enough, it's going to emit all of the colors except blue. Okay, absorption and emission are sort of the same process on a molecular level, on a level of electrons. Light comes in, it hits an electron in an atom. The electron absorbs the energy if it corresponds with an energy level transition in that atom. It's gonna, if that atom has a blue transition, that electron will accept the energy, it will absorb it, and then later on, when it goes back down to its ground state, it's going to emit out that blue light. So things that are good emitters are things that are good absorbers of light. So the best absorber of light is something that's black. It means it absorbs all colors. So the emissivity is equal to 1 for a perfect, what's called a black body. So think about like a piece of carbon, like a piece of charcoal or graphite. Carbon is very good in certain forms at absorbing light. And therefore, when it gets hot, it's also very good at emitting light. So it's counterintuitive for us because we think of something that's colored, with a black color as not as being dark, and we wouldn't think it's a good emitter, but actually it's a better emitter because it's a better absorber. So if something is a perfect black body, we don't really have anything that's a perfect black body, but our human skin is actually close to a perfect black body situation, regardless of your skin color, because we have to consider the whole spectrum of light from, infrared to ultraviolet. And we absorb something like 96%. Our emissivity is like 0.96. 0.97 when we consider the whole spectrum of light. So the emissivity is 0 for a perfect mirror. Again, it sounds a little backwards because when we look at a mirror, it's shiny. Mirrors seem bright and shiny, but that's reflected light. If we heat up a mirror, it's not really going to emit much light because it also is unable to absorb light. So anyway, this is a number. Most of the problems we do will just either give us the emissivity or assume it's a perfect black body. The sun is considered to be a perfect or a nearly perfect black body. It's a very good emitter of light and therefore a very good absorber of light, but we only see the emission side of it. So when we put all this together, we say that it's equal to a constant. This constant is the Greek letter sigma, a lowercase sigma. It's like a 0 with a hat. Sigma A E T to the 4th. So let's just try to compute. So sigma, the value of it is 5.67 times 10 to the minus 8 watts per square meter Kelvin to the fourth power. It's known as the Stefan Boltzmann same Boltzmann that we'll hear about in other contexts later on. Stefan Boltzmann, he did a lot of work. Boltzmann did a lot of work in heat, constant. And so for a human with emissivity approximately equal to 1 and a surface area of, let's just say, about 1.5 square meters. So this would be if you took all of your, a whole full outfit and you kind of rip the seams open and spread the cloth out to see how much cloth does it require to make your outfit. Different people are different sizes, but let's just say for a particular person, their surface area is about 1.5 square meters. The human body temperature is 37 degrees Celsius, which is 310 degrees Kelvin. We're going to see how quickly a human with these conditions is emitting energy. So the power is 5.67 times 10 to the minus 8 times 1.5 times an emissivity of around 1 times 310 to the fourth power. We get 785 watts. So humans we're kind of decent heaters. That's why one of the reasons why when you get under the covers, it's cold at first, but you're going to radiate heat into that space and you're going to fill it up with heat. And then you're going to be sort of in a nice, cozy, warm space. Or, if you have a partner, then sometimes their heat can be too much for you. And you just say, get away from me. You're too hot. We give off a lot of heat. However, we're also absorbing heat during that same period. So this isn't really an accurate amount if we want to think how much energy we're losing. So typically, we emit heat into our environment, but we absorb heat from our environment. So if we want to get the net heat loss, we would say, the net power is the power to emit minus the power that we absorb. So we emit with sigma A E T to the fourth. We emit using that law, but we absorb at the same rate relative to the temperature of our environment. So it has to do with the rate that the environment is sending energy to us. We put this together, we get sigma A E times T to the fourth minus the T of the environment to the fourth. So let's just say in a room at 20 degrees C, what is the net heat loss for the person in the previous example? So the net heat loss is equal to sigma. Well, let's just put our numbers in. We have 5.67 times 10 to the minus 8 times 1.5 times 1. And the temperature to the fourth power is 310 to the fourth power. And the temperature of the environment in Kelvin, 20 degrees in Kelvin, would be 293 to the fourth power. That's 150, let's round it to 159 watts. Okay, so that's actually what's happening. And the closer our environment's temperature gets to our own temperature, the less this net heat loss becomes. So if we're in an environment that's 37 degrees C, then we're not losing or gaining energy. It's just a wash with respect to radiation. However, we are mammals. We're warm-blooded, and we're always generating heat through kind of internal combustion. The food we eat is generating heat because we're mostly going to be in an environment where we're losing heat through radiation, and through convection and even conduction. So once we get to a point where the temperature is higher than our body temperature, we're kind of in trouble. We don't have a really good mechanism to get rid of that heat. Reptiles have a totally different thing going on. They don't keep a constant body temperature, but they're very good at absorbing light, and they also emit very well. There's a really cool old planet Earth with these marine iguanas on the Galapagos Islands. Has anyone seen that? Anyone seen Planet Earth? It's a really cool kind of nature documentary. I remember this was really neat because they watched these marine iguanas with thermal imaging so they could see their body temperature. And what they do, these are these giant iguanas. They basically bask on these rocks, and they're just absorbing this energy, and they basically turn bright red in the thermal imaging. And then once they're charged up, they're really hot, they dive into the ocean, and they've got like 2 minutes to try to catch a fish before their body temperature gets too cold that they can't move. So they dive in, they're swimming around. They either, if they get a fish, they climb out with the fish. If they don't get a fish, they climb out anyway. And when you see them climb out, they're like blue, and they're barely moving. They're just like creeping. It looks like they're almost frozen. They get out on the rock and they sit there for a minute or two, and that blue kind of fades and they turn orange and then red. And, this whole process takes a couple of minutes, and then they just dive back in the water again. It's pretty cool. I mean, it's a pretty interesting system, but they're operating with really thin margins. I mean, if they're in the water 1 minute too long, they're basically dead. They're too cold to even move, and they're going to drown. But they also, because of that, they barely need to eat any food at all. They don't need to be very successful hunters because they burn almost no energy. They can just sit on a rock for a week and not move, and they don't need really any energy to sustain that. Whereas we need to continually keep that energy flow going. We have my son has a bearded dragon, and he forgets to feed that thing for weeks at a time. I mean, it literally just lays there for 2 weeks, and then he'll find a cricket in the yard and throw it in. As soon as it sees the cricket, it just bursts into life, jumps on the cricket, and then it's good for another week, just from that one little bit of food. So anyway, this is just a quick kind of introduction overview to heat transfer. And